Section 2.5, Equations of Lines and Planes in Space. We have worked with lines in two dimensions, the y equals mx plus b idea. We're pretty familiar with that by now, I hope. But when it comes to a three-dimensional line, slope has to be described differently. We're used to rise over run, but in 3D, rise over run is missing the third dimension. And so we're going to talk about how to describe lines in 3 dimensions. We're also going to extend what we know about planes. So far we only know how to write planes that are parallel to the coordinate planes, but we're going to learn how to write equations of planes that maybe aren't parallel to one of those 3 coordinate planes. And then once we know how to write equations of lines and planes, we're going to take time to solve some applied problems involving distance between these kinds of objects or even angles between them. So let's get started. First, I want to make sure that we remember that parallel vectors are essentially scalar multiples of each other. If two vectors are parallel, then they have the same direction or the same unit vector, but they might just have a different magnitude. And the quickest way to write that is for two vectors u and v, which are parallel, we can write a vector equation that says that they're scalar multiples of each other. In this equation, I have the vector u, I have the vector v. We know that those two things are parallel, but then I also have this scalar k. K is the multiplier that I need so that when I multiply it to the vector v, the vectors u and k times v are equal. They have the same direction and the same magnitude. They're parallel, so we already knew they had the same direction. We just needed to make the magnitudes adjust so that they had the same magnitude. All right, we're going to use that idea to define the set of all points for which a vector made from p0 to any point p on the line. So any vector made from p0 all the way up to any point p on the line is parallel to another vector, say the vector v. Remember that a line is a set of all points that satisfies some equation. So we're going to come up with that equation. The equation is going to say that this vector p0 to p, which could be between any points on the line. Right now I have it drawn between the two given points, but I could pick another point over here and I could make a vector from p0 to that point, or I could make a point here and I could make a vector from p0 to that point. So I want to talk about all the generic points p that I can make a vector from p0 to those points p. And I want to say that that vector that I can make between p0 and p is parallel to v, which means I can have a scalar multiple equation. So that vector p0 to p, which is on the line, is a scalar multiple of the vector v, and I can see that because I'm multiplying it by a scalar t. If we replace the vectors with their component forms, then I can use the values from the point p, x, y, z, and the values from the point p0, x0, y0, z0. I can find the difference, take the terminal point minus the initial point, and I find the components for p0 to p. And then for the vector v, I'm just assigning it some generic components, a, b, c. We normally use v1, v2, v3, but I'm going to use a, b, and c. That way this lines up with our textbook. So then I plug in the a, b, c component form of the vector v, and I carry down that scalar t. In order for this equation to be true, the corresponding components have to match. So the first component in my left side of the equation has to correspond to the first component on the right side of the equation. So what I need to do is multiply the t, that scalar, into that vector v, so that I have the components ta, tb, tc. And now I can see that the first component on the left side needs to be equal to the first component on the right side. So x minus x0 needs to be equal to t times a. And that's where I come up with my first little bitty equation. I'll repeat this process where I match up the corresponding components and create a little equation. Here's my y component. And then I have one more, my z component. These three equations together make up the set of points that satisfy the original conclusion that P0 to P is parallel to V. So we call these parametric equations of a line. On the right-hand side, we have x0, y0, z0. Those came from the point that we know for a fact is on the line. And then we have a, b, c. That came from the vector v, which our line is parallel to. We have the parameter t, which is just a placeholder. That's kind of like the independent variable, but with parametric equations, we don't call that its own variable, we call it a parameter. As we let t change, the true variables, x, y, z, change with t. So we pick a value for t, plug it into all three of these equations, and then out comes a point that corresponds to x, y, z. There's a few different ways to write the equations of a line. We can use the parametric equations that we just discussed on the last slide. We can also use the symmetric equations, which essentially takes the parametric equations and solves each one of them for t. For example, if I solved the x equation for t, maybe the first thing I do is subtract x0 from both sides. And then from here, divide by a on both sides. And then I have an equation that's equal to t. Well, I could do that for any one of the three parametric equations. And then if they're all equal to t, then I can set them all equal to each other. So the symmetric equation of a line is a single equation that relates the x, y, z variables, the x naught, y naught, z naught coordinates of the point P, and then the a, b, c, which are the components of the vector v. So we have the symmetric equation is another way to write a line. And then lastly, we have what we call a vector equation. We're going to get into vector equations a lot more in chapter 3. So this will be just a kind of preview of what vector equations are. This equation takes in a parameter t, it applies some vector operations, and then the result is a vector itself. So to make the vector equation of a line, we find the position vector that coordinates to the point P, so that would go from the origin to the point P. That's a position vector because it starts at the origin. And then we take the vector v, the vector that our line is parallel to, and we multiply that to a parameter t. So that's the vector equation for a line. Again, we'll get more into vector equations later. That's just a preview for now. Let's try finding the equation of a line that is parallel to some vector v. Here we're given v has the components -4, 1, and 2. And then we're also told that our line passes through the point P. Notice that the definition for a line requires these two bits of information. We need a parallel vector, and we also need a point. Without those two things, we cannot write the equation of a line, no matter which of the three versions we decide to use. So we have the two bits of information we need. Let's get to it. If we want to do the parametric equations, then we can write out our x equals, y equals, and z equals. We know that we'll have all three of them. These equations take in the coordinates from the point P. So we're going to take from our point P x0 has to be 1, y0 has to be 4, and z0 has to be -2. So we'll plug those into our equations. I wrote that too small. X equals x0, that would be 1 plus t times the component a from the vector v. So from this vector, we can see a is equal to -4, b is 1, and c has to be 2. So for the x equation, we'll have x0, which is 1, plus t times a, which is -4. And we can clean that up a little bit. We can write that as x equals 1 minus 4t. That looks a little cleaner. And we'll do the same thing for the y equation. Take the y0 plus t times b. And if we can clean that up, we will. And then the z equation, z0 plus t times c. And clean that up if we can. I'm going to write that as 2t minus 2 because I don't like having negatives for my first value. So these three small equations describe the line that is parallel to the vector v and passes through the point P. Let's try another example. This time, we're not exactly given the two things that we need to create the equation of a line. Remember that no matter which version of a line equation we use, we always need the parallel vector v, and we need the point that the line passes through, P. Here, we're given 2 points and no vectors. But that's not a problem because we can create a vector v that is literally on the line. So if I know that these are the 2 points that they're giving me, and they're asking me to find the line that passes through those 2 points, I can create a vector between those 2 points. And that vector, because it's literally on the line, it absolutely is parallel to the line. So that's what we'll do. We'll first create the vector v by using any arrangement of these 2 points. It doesn't matter what you call the terminal point and what you call the initial point, because heck, if I had drawn this vector pointing the other way, it's still parallel to the line. So that's good news. Doesn't matter which way we do it, just stay consistent. I'm going to do the last point minus the first. So I'll call this my terminal point and I'll call this my initial point. And then we'll simplify to find the components there. And now that I have the vector that I'm parallel to, I just need to pick one of the 2 points that is definitely on the line and plug it into the symmetric equations. This problem asked for symmetric. So using the vector v that we just found, and I'm going to pick that initial point as my point P. I'll plug these into the symmetric equations. All right, so I've plugged in x0 to be 1, y0 to be 4, and z0 to be -2, and that all came from the point P that we know is on the line because it was given that way. And then I also plugged in -4 for A, 1 for B, and -2 for C. There's a little bit of cleaning up that can be done here, but not much. There's not a whole lot of point in moving the negative up to the numerator. We could and should simplify the double negative in this z equation to be z plus. Now that being said, if you are looking at the symmetric equations of a line and you see a plus sign in the numerator, that should indicate to you that the coordinates of the point P had a negative value. So be careful there. The minuses are built into the equations. Notice the minus is built into the equation, and if you plug negatives in, the minus becomes a positive. For this same problem, if we had set up the parametric equations of a line, then we would write x, y, z, and plug in each of the values that we know. So x0, y0, z0, and then add to that the t times components of vector v. So the parametric equations and the symmetric equation, they're describing the exact same set of points, just using different ways to do that. We have one more example on this slide, and this one is very similar to what we just did, except for we're looking for a line segment here. Remember the difference between a line and a line segment. A line gets to continue indefinitely in both directions. There's no starting or stopping point for a line. For a line segment, there is. At one point, you're either at the beginning or the end of the line, and the other point would be the opposite. Now the segment falls on the same path as the line, but we need to restrict the parameter values so that we don't generate points that are on the line, but not the line segment. Now, if you pay close attention, the points that we are trying to make the line segment between are the exact same points that we used in the example on the left side of the screen. So that's great because we know the parallel vector v. We've already calculated it. And we know that these 2 points are on the line segment, so we could use either one of those as our point P. I'm going to use the same one we did in the last one. And then the last thing we need to do is just figure out how to restrict T. So we're literally going to use the exact same parametric equation. The only thing that we need to do in addition to that is state what values of T will give us the set of points on the line segment and nothing extra. So looking at this, if I plug in t equals 0, then I'm right at the point P. That's at t equals 0. So if I plug in 0, 0, 0, I get the point 1, 4, negative 2. And if I allow t to increase up to 1, then I would be at that second point. If I plug in 1, I have 1 minus 4, which is negative 3, 4 plus 1, which is 5, and then negative 2 minus another 2. Oh boy, I just found a mistake. This is what you're missing from live lectures, is watching Professor Reale make mistakes. So in this z equation, I know that I just found a mistake because when I plug in t equals 1, I should land at that last point, which would give me a 0, but negative 2 minus 2 is not 0, which means I made a sign error. So let's go back and hunt for it. This is good practice, right? If I look back to the very first thing we did, we calculated the vector v doing subtraction. So negative 3 minus 1, that looks good. Positive 5 minus positive 4, that looks good. 0 minus negative 2, that should be plus 2. So all of the z components that had the negative 2 in them need to be corrected. Oops, not that negative 2. This negative 2 should be a positive because that came from our v vector that we calculated. I need to fix that in the parametric equation as well, and then we'll fix that here. Whew, that was a close call. Glad we caught that. So now if I plug 0 in for this parameter t, I do get the z value of 0, which matches that second point, the ending point of our line segment. So now all we need to do is add to our equations the range of t values that we can use. If I plug in a value of t that is larger than 1, then I'm going to be on what used to be the line past the end point of my line segment. So all we need to do is add into here that t is allowed to go from 0 to 1. And the exact same thing could be tacked on to the symmetric equations so that that symmetric equation represents a line segment rather than the entire line. So keep in mind a line continues infinitely, all values of t are acceptable for the parametric or symmetric equations of a line, but when it comes to a line segment, we need to restrict the values of our parameter t so that we're only talking about the set of points that are on the line segment.